In this video, we are going to see what is Bernoullis equation. I have drawn a figure before you. This is basically a water tube or liquid, and a liquid is there, and these are the streamlines. Correct? Now water is flowing inside the tube through this end, and it is coming out from this end. Here at B end, the pressure is P1 and area is A1, and at the E end, the pressure is P2 and area is A2. Now let us consider the liquid lying between B and D. This liquid, it is advancing to C, and here from D to E. In delta T time, this liquid is advancing to C, so that this distance will be, suppose velocity is V1, then it is V1 delta T. Means in delta T time, this will advance this distance. Correct? Now the same amount of liquid will come out from D end, it will advance from D, and suppose here at D velocity is V2, then it will be V2 into delta T. Delta T is very small, so it will advance V2 into delta T distance, because we know that delta X upon delta T is basically velocity. So this is the distance we are talking about, V1 delta T and V2 delta T. Now, when it is advancing a distance of V1 delta T at this end, then what will be the work done? Work done is basically force into distance, or you can write it as delta X. Force is nothing but P, pressure, into area, into delta X. So this is the basically work done at point B. So work done at point B will be your P1. Here A is A1 and delta X is nothing but V1 delta T. Correct? Now what is this? This is the volume of the liquid advancing in time delta T. Correct? So you can say in this fashion that this much work is required for moving the liquid from B to C at B end. Likewise, at the further end, W2 will be P2 into A2 V2 delta T, or correct, delta V is same because in delta T, whatever liquid is advancing, the same is coming out. So in both the cases, delta V will be same. So what is the total work done? Total work done will be W1 minus W2. And this we can write it as P1 minus P2 into delta V. Why W1 minus W2? Because W1 is a positive work done, and whereas W2 is the negative work done, because at the farther end, at the output side, the system is doing the work. It is getting the liquid outside. You don't have to do any work. But of course, at the B end, at the initial end, you have to do some work. And basically, this work is being done by the surrounding fluid. Correct? Now, this total work done must bring some change in other energies. Because when there is a change, when you are doing some work, then there must be some change in the energies. So what is that change? Basically, one is change in kinetic energy. What will be that? You know, kinetic energy half mv square. Here it will be half rho VT square minus V1 square. This is the change in kinetic energy from end B to end E. Got my point? And of course, there is an elevation also. This tube is rising with respect to ground. Here the height is h1. Here the height is h2. So there will be change in potential energy also. What is that? That is mgh. mgh we can write rho g h2 minus h1 into delta V. This is here also. Delta V will be there because m is what here? Rho into delta V. In mgh also m is what? Rho into delta V. Correct? Now delta V, it will cancel out. And if you rearrange, then what? It will give P1 plus half rho V1 square, this is velocity, plus rho G H1 equal to V2 plus half rho V2 square plus rho G H2. Correct? So one is this end and two is this end, correct? So at one end, P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. That means the sum of this remains same. That means we can write it as P is pressure plus half rho V square plus rho G H. This remains constant. Correct? From this equation, this is equal at this point. At this point, that means at all other points, the sum total of pressure plus half rho V square plus rho GH will remain constant. And this is basically Bernoullis equation. It has got very wide applications. It's very important equation. And this equation has been given by a Swiss physicist, Daniel Bernoullis.